So clearly, the unsolubility of nonpolar substances in water is largely an entropically driven or undriven event. So, summarizing, the free energy is negative for solvent equal to organic solvents to water. I'm sorry, this is for the gas to the solvent. This is negative, it's favorable when we have an organic solvent. The free energy is positive when the solvent is water, it's unfavorable. The enthalpy is negative for all solvents, including water, and it's exceptionally favorable in water. Exceptionally favorable in water. The entropy is negative, and that is unfavorable, and about the same in organics, and the entropy in water, for the gas in water, is much more negative, much more unfavorable than in the organic solvent. Let's go back to Breslau's paper. The hydrophobic effect is the tendency of nonpolar species to aggregate in water solutions so as to decrease the hydrocarbon water interfacial areas. It reflects, in part, the large cohesive energy of water, whose molecules would better bind to each other than to hydrocarbon surfaces. If that's true, why is the enthalpy of solution of xenon in water favorable? And it's even more favorable than is the enthalpy of solution in the organic solvents. This statement is not right. It's wrong. It cannot be correct given simple thermodynamic measurements that have been around for 3 decades, more or less. So I'm not sure he's got a really good grasp on what the hydrophobic effect is. It's not reflecting the large cohesive energy density of water. It's not entirely reflecting that. So what is Breslau really saying? He's saying that all of the processes that he listed, micellization, cell membranes, binding of proteins to substrates and antigens to antibodies, and are driven by the hydrophobic effect, which he claims is mainly due to the very unfavorable process of making a cavity in water, which is recovered when the 2 nonpolar species associate or leave the water phase to enter a lower polarity solvent. He's saying it's all driven by the energy you're going to get back. The energy, the enthalpy that you get back when the cavity in water collapses and the water gets back to being water and the solute leaves the water phase. That's his interpretation. The most famous book on the hydrophobic effect is a book by Charles Tanford called The Hydrophobic Effect. And this is in the preface of the book. It's not even inside the book. It's like there's the title page and there's the preface. And Tanford says, the existence of hydrophobic substances and of organic molecules of a dual nature, meaning surfactants that have a polar end and a non-polar end, containing hydrophobic portions, has been known for a long time, but misconceptions about the origin of the phenomenon persisted until quite recently. McBain, who was a guy who studied these processes several decades before Tanford's time, McBain mistakenly believed that the association between hydrocarbon chains and the formation of such micelles arises from like-to-like attraction. In other words, the lipid part of the molecule associated with the lipid part of the solvent. That's what McBain said, and Tanford's saying that's a mistake. implying that the attraction of hydrocarbon chains for each other plays an important role in this process. By calling this a mistake, Hanford's saying that the attraction of the nonpolar chain for the other nonpolar chain does not play an important part in the process. He couldn't live with leaving, taking a shot at McBain, so he took a shot at Peter Debye, and that's not a good idea. Even Debye evidently shared this mistaken belief. In other words, he says Debye thought it was due to the like-to-like process, not the dislike of the water. Okay. So now let's get into reverse phase chromatography. Here's a simple partition model of reverse phase chromatography. It's a partition model. You've seen this cartoon before. By adopting this cartoon, we're saying that surface interactions are not important in reverse phase chromatography. It's just a question of the relative solubility of the solute, the analyte, for the water phase and the nonpolar phase that governs this distribution coefficient. Here's a little different picture of the reverse phase process. This cartoon is from a paper by Dorsey and Dill. It's their cartoon representing the difference between a partition model and an absorption model. So when a solute molecule transfers out of the mobile phase into the stationary phase, there's two possibilities. There's actually more than two possibilities, but we're going to keep it simple. Either the solute molecule becomes embedded, surrounded by the chains, or it just sits at the interface between the stationary phase and the mobile phase that's up here. This is what we would call a partitioning model. This is what we would call an absorption model. Okay, now Dorsey and Dill did something very clever. They said, let's choose a very simple model of the stuff on the surface. We're gonna make believe that it's a cubic lattice. Okay, so there's a lattice. And so here's the RP chunks of the reversed stationary phase glued onto the surface. And here's our solute. And it's a cubic lattice in 3 dimensions. So right above the solute, there's another chunk of reverse phase. And right below it, there's another chunk of reverse phase. And so the ratio of interactions here is like 6 to 1 when the solute is fully embedded in a cubic lattice. But, went the wrong way. If the solute's not embedded in the lattice, it's really interacting with the mobile phase, and only one side of it is contacting the stationary phase. So that's going to impact the way we're going to look at our data later on. I just thought I would mention what a cubic lattice is. But of course, it's not really a cubic lattice. It's a much more elaborate structure than that. This is one way you could draw the reverse phase. If the pore in the silica were 60 angstroms, and we had a C18 chain, And if the C18 chain was all, and if all the bonds in that were in a fully trans conformation, that would be about 20 angstroms. So we'd have 20 angstroms of bonded phase here, we'd have 20 angstroms of bonded phase here, 60 angstrom pore, we have about 20 angstroms of mobile phase left. So we're talking about a solute molecule moving from this stuff into that stuff. This is a lot more complicated than a cubic lattice. So no wonder people don't know whether this is a partition mechanism or an adsorption-like mechanism. Here's an infinitely more elaborate model. I don't know how many hours of computational time was spent to generate this figure. It was a lot. This stuff is silica. These are C18 chains that have been attached to the silica, randomly attached, and allowed to come to an equilibrium situation with regard to one another and with regard to the mobile phase that's in the middle of this pore. Some of the mobile phase has attractions to the surface, so there's some mobile phase. That's actually mobile phase that's inside the C18 chains, but most of this mobile phase is really right close to the silica surface. But some of it certainly dissolves into the chains, just like we talked about last week when we were talking about the fact that the apparent dead volume of the column changes, and that was due to adsorption of water and of methanol. By the way, this is a methanol-water mixture that this is equilibrated with. So we're talking about an extremely complex situation, and the question is, does the solute come down in here, or does it hang out in that area? If we simplify this grossly by taking a cubic lattice, in one case we have a 1-to-1 interaction, and in the other case we have a 6-to-1 interaction if it's embedded in the chains. Okay, so those are the issues. What is the driving force of reverse phase liquid chromatography, and is it an adsorption or is it a partitioning model? The first model that really captured a lot of attention was the Horvath model for the hydrophobic solute partitioning into the reverse liquid phase. Horvath, of course, is one of the inventors of liquid chromatography. He died a few years back, about 5 years ago. I found it absurd that he did not get a Nobel Prize when John Fenn got a Nobel Prize for inventing a detector for liquid chromatography, namely the ion spray detector. Kind of weird, in my opinion. Not that Fenn didn't deserve it, he did, but Horvath and others deserved a Nobel Prize for HPLC. Here's the Horvath solvophobic model. Now, Chaba, that's his first name, really had a great colleague. Fenn, by the way, was a colleague of Horvath's at Yale. But he had another great colleague at Yale in the chemical physics department by the name of Oktay Sinanoglu, who was a biophysicist who really developed a highly quantitative model of the hydrophobic effect. And Horvath didn't call it the hydrophobic model, he called it the solvophobic model because we don't use just water. We use methanol water, acetonitrile water, and so on, so he called it the solvophobic model. But this was the basic idea of the hydrophobic / solvophobic model. So we have this surface ligand bonded to the silica, and that ligand has lots of solvent around it. This is maybe too much solvent, but that was his picture. And here's our solute molecule, and it's out in the mobile phase, and it's got lots of mobile phase around it. So this is the situation before the solute enters the stationary phase and becomes bound to the stationary phase. After the solute binds to the stationary phase, you see, there's got to be a bunch of solvent that gets liberated, that gets, if you will, squeezed out from between the nonpolar parts of the stationary phase and the nonpolar parts of the solute molecule. And it's the energy liberated, the free energy liberated, when this happens, that is the driving force in the solvophobic model. It's because the solute is no longer in this nasty, horrible stuff called water. It's getting out of water that is providing most of the free energy that drives the process forward. That's the solvophobic model. And they were able to quantify it. I really said this, and I'm going to skip ahead. Specifically, the model was set up in terms of the polar and nonpolar surface area of the solute molecules. So here's random solute molecule. We would not count this as part of the nonpolar part of the molecule. We wouldn't count that. We wouldn't count that. What we're concerned with are the nonpolar parts of molecules, not the polar parts, in this model. And so what the Horvath model leads to is the free energy of retention is equal to the surface tension of the solvent. Actually, it's a microscopic surface tension of the solvent times the change in the nonpolar surface area of the ligand and the solute when they're separate, and the ligand and the solute when they have become associated. So this delta A here is the change in this area relative to that area. So you see we have a decrease in the nonpolar surface area that's exposed to water by binding. And the bigger that change is, the more negative the free energy of retention is. So the more negative the free energy of retention, the more that stuff should be retained. Also, the higher the surface tension of the mobile phase, the gamma times delta A is the free energy that you get when you decrease the area. That gamma is the surface tension. The more surface tension, the more free energy that's going to get liberated when the binding process goes on. And this is effectively the cavity term that's driving the process. And in addition, we have a whole bunch of electrostatic processes like London interactions, dipole-dipole interactions, dipole-induced dipole interactions, and perhaps even Coulombic interactions. And they may or may not be favorable, but this is a favorable process. And the bigger this is, the more favorable it is. And the higher the surface tension of the mobile phase, the more favorable the free energy transfer is. So let's measure a bunch of retention factors, and we'll take the logarithm. And RT times the logarithm, of course, is a free energy. And relate that to the hydrocarbonaceous or nonpolar surface area of the solute molecule. And we'll do it for acids, which are negatively charged. We'll do it for amines, which are positively charged. And we'll do it for zwitterionic amino acids, which are neutral. And we get three nice straight lines. They're offset from one another because they have different charges. But the charges can be accounted for by a simple Debye-Huckel type of equation, inter-ionic interaction equation. And so we can merge all three different kinds of molecules, positive, negatives, and neutrals, into a single plot of log K prime versus hydrocarbonaceous materials that really run a pretty big range in solutes. There's your delta A is proportional to that. Looks good. Okay, let's do things to the mobile phase to change its surface tension. If I add methanol to water, the surface tension goes down. If I add acetonitrile to water, the surface tension goes down. And it goes down more for acetonitrile than methanol. And if I had THF, it would go down even further. And this is fitting with what we said the other day about the relative strength of solvents. Methanol is weaker than acetonitrile. It has a smaller effect on the surface tension. THF is even more nonpolar. The surface tension goes down even more. It's also consistent with the salting out coefficients. As we increase the salt concentration, the surface tension goes up linearly. If the surface tension goes up, you're going to force the nonpolar solutes more into the nonpolar environment. So this is all consistent with the solvophobic hydrophobic model of reverse phase chromatography. Here's the plot I showed you. They have log K versus potassium chloride concentration, but we could just as well plot that against